Hey everybody, welcome to my talk about BUP. I think I'll be pretty short on time, so please ask questions on Twitter, use these hashtags if you have any questions. I am Zoran Saric, I study computer science at TU Darmstadt, and I'm involved in BUP since April of 2010. I'll first give a little motivation on what to do with backup, what our goals with backup are. Then I'll go to detail on Git's file structure, and then I'll show you what BUP is. Okay, backups. Yeah, sure, we want to do backups, and we want to have our data, and it shouldn't be corrupted. And yeah, we want to have space-efficient backups. So we don't want to have complete copies, full copies of every backup we do. This would fill up our hard drives pretty soon. So space efficiency. Second is we want to have convenient access to our backups. It doesn't help if we have 10 years of backups in one tar file and have to download 200 gigs to get 2 files back. Third, we want to be safe against bit rot, against those small changes on disks that break our files. That isn't too good. We want to be safe against that. And we want to be sure that nobody can change the history of our backups. So if somebody infiltrates our system and they change anything in our backups, we want to know that they did this. Who of you knows Git? Great. Who of you knows the internals of Git? Okay, fine. This shouldn't be news to you. Git is a distributed version control system. Is anybody here that needs an explanation on this? Okay, cool. It is content addressed. In Git you have these SHA-1 hashes, and everything is addressed by a SHA-1. Every content, every commit, everything. Every object, every commit, and I'll go into detail on this, is immutable. You save something to Git, and it is never changed. And Git is snapshot-based, not like Subversion, diff-based. It is snapshot-based, and this makes it pretty fast. Okay, let's take a look at a Git repository, or better, its objects. First, we have blobs. Blobs are really content. No files, like any file that contains hello world and has a file name, but only the content hello world. Second objects are trees. Trees are kind of like file system directories. They have references to blobs and other trees. So with trees you can build trees. Yo, dog. Third are commits. Yeah, you probably know what a commit is. Commits are snapshots of the state of a repository at some point in time. They first always have a reference to a tree, and they might have a reference to a parent, unless they are the most recent commit. And fourth, we have tags and branches. Tags and branches are references to commits, and they are just plain text files. So by default, you have a master branch, and this master branch is a file in your Git repository, in your Git directory, and it contains a SHA-1 in ASCII. You can retrieve the commit with this. This is how a Git repository looks like, the tree of a Git repository. First we have master, the branch, which is a reference to some commit. This commit has a reference to a tree and to its parent, and the tree has references to blobs. And you see, because we are content addressed and we have immutable objects, we can reuse objects. So this might be the README of some project, and it didn't change. So both trees, both commits, use the same blob. This is pretty neat. This brings deduplication on the file level, which is nice for a backup. Last objects are pack files. If you do a commit in your Git repository, every object is written to .git objects, and they are loose objects, they are single files, which is nice for the start, but once you have a lot of them, it gets really expensive to retrieve them because you have to look up every inode, and this is expensive. So we have pack files. Pack files are just objects written one after another in one big file. They are up to 2 gigs, and you can do a sequential read if you retrieve more than one blob or more than one object at a time, and this is pretty fast. Indeed, this is faster than a copy on the file system. Okay, sounds pretty great. Why don't we do backups with Git? Just plain Git, and I guess some of you might have had that idea. Hey, Git is great, and it does deduplication, and it is all small, and I'll use it. And here I have this 200 gig SQL dump, and I throw it at Git, and damn it, it's slow. When writing pack files, Git throws both versions of a file through xdelta. And if you know xdelta, you know that xdelta has the assumption that both versions fit into memory. And this is fine for most source code, and this might be fine for JPEG files. But if you have, like I said, a 200 gig SQL dump or some VMware image or anything, it gets pretty slow and memory hungry. Second, Git doesn't store metadata. Okay, it stores the executable flag, and it stores symlinks, but nothing else. No permissions, no owners, no groups, no ACLs, nothing. That brings us to BUP. Yay. BUP is a software that uses the Git file format. It is developed by Avery Penneroon, which also developed Git subtree, S-shuttle, redo. That's the URL of the project. Everything development regarding is done over the mailing list. We have no bug tracker. We don't do pull requests on the GitHub. Patches are sent to the mailing list. Yeah, that's the heart of the project. At the moment, BUP isn't production ready yet, I'd say. There's a Debian package, but you know Debian packages are pretty old. And you want to be pretty bleeding edge with BUP. So you better clone the repository and make it no configure step required. Yeah, and of course we have some dependencies. Let's take a look how BUP is used. Currently, a backup action is done with 2 steps. First, an index step. The index step traverses the file system, takes a look at every file, and writes it to an index. And you can tell if you need to back it up, or if you know it already, if you have backed it up already. And the save step traverses this index. This has the advantage that we have a progress bar that is reliable, not like a Windows progress bar, if you know the XKCD. Yeah, the save step traverses the index, writes all needed stuff to the repository, and creates a commit. Third command is backing up to a server. This is done over SSH, so you can do push-style backups to a remote machine. This is doing a backup of a server to your local machine, so you can do pull-style backups too. With the on command, you can run commands on a remote server. You have to have BUP installed. There, of course, you have to have SSH configured, and then you do the index step, and you do your save step, and you have your backups locally. This is how you can take a look at your backup. This is my backup set, the name of the backup. This is a symlink to the latest backup, and this is my home directory. Okay, let's take a look at BUP's features. Deduplication.
Can you also restore your backup?
Yeah. Funny fact, the restore command is there since 0.23, I think. There was ways to restore single files before, but restoring a complete backup is pretty new. Okay, first feature is deduplication. You know, one of our motivations is to have space-efficient backups. This is the link to a mailing list thread that discusses some benchmarks I did. Somebody came to the mailing list and said, okay, I use rsnapshot, why should I use bub? Yeah. Then I sat down and made a benchmark. I started to Amazon EC2 machines with Debian, put some random data there and changed a bit in it on both machines, did my backups, and you can read it on the thread. Our snapshot had 4.97 gigs, bub 2.18. I also did an import of my rsnapshot backup. At the moment, I use rsnapshot for my production backups. And yeah, my rsnapshot backups are 12.6 gig, and bub fits it into 4.6. We have metadata support, kinda almost done. In fact, we have a working patch set that is just about to be merged into master since half of a year, I think. Yeah, if you do something, we want to do it right, and we want to have it tested, and we want to be sure it works for 100% because it's backups, and you don't want to have your backups messed up. So we don't only store owner and permissions, but we store exact times, as exact as the file system we're backing up of, gives us the timestamps, permissions, extended ACLs, and SE links attributes. Nice feature is a fuse module. You can mount your backup with a fuse module and can browse it with your file manager. You can restore files from your file manager, just copy them out. Or you can also, I think here are some sysadmins too, and often you have somebody who says, oh no, I deleted that file and I need it back. And you can just say, okay, here's your backup, just mount this Samba share and get it yourself. Nice feature too is a web interface. You can browse your backups with a nice web interface with your browser and also retrieve files from there. It runs on DDWRT. So yeah, you can in fact, I thought about leaving that slide out. Yeah, you can run it on your router, on your NAS, whatever. Pretty neat. We have an import script for rsnapshot. So if you're using rsnapshot right now and think about using bub from tomorrow on or from next year on or whatever, there's a script for it, and it doesn't just save your rsnapshot tree, but it also creates commits with the correct timestamps. Probably more will follow. I heard duplicity is pretty widely used too, so I think I'll write a duplicity importer. We are fully compatible with Git. You can use the Git binaries to access data in a bub backup. You can look at your backups with gitk, gitx, tig, you name it. This is something that's pretty important to us too, because we might someday say, okay, bub isn't interesting to us. You can always fork it. It's LGPL. But you can always access your data with Git too. And if you remember, one of our motivations is to be safe against bit rot and failing media. For this, we use part2. Part2 creates parity information, so you can restore files if some bits are broken. Yeah. Okay, let's take a look how bub does things, the algorithms and data structures. We have hash splitting, MIDIX, and Bloom filters. Okay, what is hash splitting and how do we do deduplication? I have to say, we don't do deduplication only on a file level, like Git does it. We go deeper and split files into chunks. So if you have a 200 gig SQL dump and add one line in the middle, you don't have to copy, don't have a full copy of that file, but only the changes. And this is done with hash splitting. We use a rolling checksum algorithm, the one that's used in rsync too. Who's familiar with rsync? Okay. Rsync is a tool you can use to copy big files to some server or anywhere, and it only transfers the deltas. So if you have a 200 gig SQL dump and change one line and want to upload it again, you can use rsync. We use this algorithm. A rolling checksum is an algorithm that iterates over a file with a window and calculates some hash sum based on a window. And if this hash sum, hash sum is again only dependent of the content, not of some fixed size window or anything. And if this hash sum has 11 ones in the least significant bits, we create a new chunk. Why 11? Don't ask us. If you have a better number, come to the mailing list and help us. Computer science to the rescue. So we have an average 8 kilobyte chunks and save big files in 8 kilobyte chunks. So this is how we get deduplication. Do you remember the pack files in Git? Every pack file is just objects written out one after another, and index files are indices for these pack files. If you want to look up an object in a pack file, you need about 3 to 4 lookups per pack file. In a big backup set, you can have several pack files. And if you do backups, you want to check, do I know this blob or do I know this tree? Okay, I have to iterate over all pack files. I didn't find it. Next pack file, I didn't find it. 3 to 4 lookups per pack file. If you divide, I don't know, 200 gigs by 8 kilobytes, you know how many objects you get. And this is many lookups. We have MIDX for this. MIDX is an index for several pack files, and an object is found in about 2 lookups. The only problem is, if you add something to your repository, you have to rewrite the complete MIDX file. And this takes some time too. So we use Bloom filters. Who of you knows Bloom filters? Okay. Bloom filters are a probabilistic data structure. You can check if you have seen a datum before with a given probability. The probability is the probability for false positives. At first, this sounds weird. Why do you use something that has a false positive rate? But they are pretty fast, and you can append to them. And you can calculate how big your probability of a false positive is. And if we have a probability of bigger than 1%, we just recreate the Bloom filter. A Bloom filter is a bit array. You know bit arrays? They are just arrays of bits. No. No, you have some binary memory, and you set bits in there, and you want to use a hash function that is optimized to have least ones in the result as possible. And the Bloom filter, this bit array, is then used by using the existing bit array and adding the new ones with OR, bitwise OR. Yeah. When a hit is found, we do a MIDX lookup to be sure that we don't have a false positive and we don't skip an object that we need. Okay. Recently, We have, like I said, metadata support about to be finished. It's available. You can use it. It's publicly available. Sorry. You can test it. If you're into Python, BUP is developed in Python. Join us. Write tests. I recently wrote a repack patch set. Before this, it wasn't possible to get rid of old backups. So you added your new backups, and you added your new backups, and there was no way to get rid of them. In fact, this isn't a trivial thing. You have to get all references to objects you need, and then rewrite all pack files. We have inotify-based daemon discussed at the moment on the mailing list. Inotify is a kernel module that notifies you if files are changed. And you can say, okay, I want to monitor my home directory, and every time something is changed, I want to have it backed up. This might result in a lot of commits, but your hourly or half-hourly or whatever interval you choose, backups will be very, very fast then, because nothing has to be saved, and just a new commit is done, and you can throw away the inotify branch later, and yeah. Don't ask what BUP can do for you. You know it? Yeah, it's Python. Performance critical parts like calculating the rolling checksum are implemented in C. We don't have a native Windows support port. BUP runs in Cygwin, fine. I already backed up Windows systems with it. But yeah, if you're into Python and Windows, join us. Also, we don't have metadata support for OS X or Windows. OS X has, I think it's called FS event, which is something like inotify. You could port the inotify daemon to it. We are pretty short on end-user interfaces. Like you saw in the examples, backing things up is an index step and a save step. This will probably get done with one command later, but we don't have GUI, we don't have nice diff. This is stuff that you can do if you want to. Yeah. Yeah, that's pretty new. I didn't have time to look into it, but it looks pretty neat. Sorry? Yeah, the question or interruption was there's a there's a KDE interface to BUP that's pretty new. Yeah, I didn't have time to look too deeply into it, but the screenshots look nice. What's so funny about that? Thanks. This is how you can contact me. Spam me on Twitter or contact me on Freenode or Hackend. Yeah, I think we have some time for questions, if there's some.
Yeah, very few minutes, like maybe 2 short questions or something. I think we start with one from ISE.
Like I said, if you have more questions, either grab me here, I'll be around for a moment, or use the hashtags BUP and 28C3 on Twitter.
Salz and Orion RC are asking, does BUP work with special files? So can you back up / the root directory?
You can back up your /root directory, but devices aren't saved yet, so no special files, no.
Okay, there was a question over there.
You can back up dev urandom though. Might take some time.
Does it work? Yeah. How is the repack? How is it implemented? Because I can imagine that if you remove dependent files from later commits may depend on blobs that are very early introduced into the system.
Yeah. What I do is I traverse the commit history. I traverse the whole tree. and keep references to objects that I've seen. And then I go to my pack files and write every object that I've seen that I need to new pack files. That's not trivial. If you have a big backup and you just save your SHA-1s to a list or anything, you probably will run out of memory. So I use bit arrays again. And
So the Bloom filter step is repeated then?
no, I don't do hashing. For every pack file, I have a bit array, and I set the bits of objects that I need.
So, okay, maybe one last question.
When you said you provide deduplication on subfile level, how do you generate those objects? Because the Git objects are big chunks of a whole file, and how do you split them and still be compatible with the Git format?
We split big files into trees and blobs again. So if you have some dump.sql in your backup, in your Git repository, there'll be a dump.sql.bub, and this is a tree that points to trees and blobs. So if you access big files with plain Git, you'll get those chunks, but there's a one-liner on the mailing list that packs them together again. So if everything breaks, you'll get it back.
Okay, time's over. Thank you, Zoran.